Any questions on anything at all before we get started? We're back into it again, I should say. Good so far? Okay. All right, so last time we started talking about how we extend the trig functions to angles other than acute angles. So we talked about, pardon me. So we talked about how we do reference angles and those kinds of things. So just as a brief reminder again, if we know, basically the whole idea is that if we know the values for sine and cosine on 0 to 90 or 0 to pi over 2, we can figure out everything else because everything else can be written in terms of sines and cosines, right? So if we go 0 to pi over 2, I think I wrote it with degrees last time. But we'll do it in radians in this time. So if we've got theta is 0, what is sine of 0? 0, and cosine is 1, right? And then we start going with the other ones. Pi over 6 is going to be for sine. One half, good. And for cosine, it'll be good. Square root of 3 over 2. For pi over 4, square root of 2 over 2 or 1 over root 2, whichever way you want to think of it. Doesn't matter to me. For pi over 3, good. And for pi over 2, good. Yep. Sine is 1 and cosine is 0. Good. Perhaps an easy-ish way to do this, just write your numbers from 0 to 4. I should say your integers from 0 to 4. Start there. Divide by 4 all the way down. And then take your square roots. Notice that the first one gives you 0. The second one gives you 1/2. The second one gives you root 2 over 2. This one gives you root 3 over 2. And this one gives you 1. Those are your sine values from 0 to 90. And then the cosines are flipped. I mean, not flipped over, but flipped in the reverse order. Cosine is decreasing. The cosine was increasing. So again, an easy straight. I mean, if you're having trouble memorizing them, it's a nice little memory device to help you. Go from 0 to 4, divide everything by 4, take the square root. That gives you the values for sine. And again, for cosine, you just read up instead of reading down. So sine of 0, sine of pi over 6, sine of pi over 4, pi over 3, pi over 2. And then cosine 0, pi over 6, pi over 4, pi over 3, pi over 2. So again, if you're having trouble memorizing them all, this is just a quick way to be able to get them all written down. If you hate it, then don't do it. This is just a side note, if you will. From a sheer number standpoint, it's a nice curiosity that it works that way. All right. Anyway, so those were our exact values for sine and cosine, but these are also the ones that we use for reference angles, right? Remember, our reference angle is the acute angle that we can make when we drop our perpendicular down to the x-axis and make that little reference triangle. And then we use whether or not we are left or right or up or down to determine if we're positive or negative, right? So again, let's just review one before we go back to the quadrant angles again. If you were asked to do sine of 7 pi over 6 to start with, remember when it's in radians, the reference angle, if it's a pi over 3, 4, or 6 is pretty straightforward, right? What is the reference angle here? Pi over 6, right? Well, you can just ignore the number that's out in front if it's in lowest terms, right? Okay, so our reference angle is pi over 6. So we know that this is either going to be positive sine of pi over 6 or negative sine of pi over 6, right? So our only thing that we have to worry about is it positive or is it negative? So if we think about the picture again, all the way to here is pi, which is 6 pi over 6. So we go a little bit further. So what quadrant did we end up in? 3, right? Sine is opposite over hypotenuse. Our opposite side will be negative in that case. So it'll be negative sine of pi over 6. And then sine of pi over 6, we just said a second ago, was what? 1/2. Yep. That okay? If you wanted to do something like cotangent of negative 4 pi over 3, say, again, reference angle is pi over 3, right? So it'll either be positive cotangent of pi over 3 or negative cotangent of pi over 3, one or the other, right? Okay. So again, go to our picture. Let's figure out what quadrant we're in. It's negative, so we'll start going downward this way. That's 3 pi over 3, so we got to go one more. So what quadrant are we in? 2, right? If we're in quadrant 2 and we think about our reference triangle, and we'll do more of these today as well when we do some other types of problems. If we think about our reference triangle, your opposite side, is that positive or negative? Positive, because we're above the x-axis, right? But your adjacent side is negative. So cotangent is going to be positive divided by negative, so it'll be negative, right? So our cotangent of negative pi over 3 is the same as negative of cotangent of pi over 3. And I don't expect you to memorize the cotangent off the top of your head, but we should know how to rewrite it in terms of sine and cosine, right? Cotangent, in terms of sine and cosine, what's cotangent? Yeah, cosine over sine. Cosine of pi over 3 is, and sine of pi over 3 is root 3 over 2. And if we simplify, we get 1 over root 3. And if you want to rationalize, it's root 3 over 3. But notice we can get everything down to sine and cosine between 0 and 90. Every single problem that you do, you can always get down to sine and cosine between 0 and 90 when you're doing these. You don't have to memorize a whole bunch of values for a whole bunch of different angles. You need to know 5 of them. And if you remember the little trick, you don't even have to memorize them. You just have to remember the trick. Save some brain space. You got more important things to worry about. Right? When's the new Taco Bell delight going to come out? Right? There are more important things to worry about than memorizing 8,000 different values of angles. Is it okay? Okay. So this review is a little bit about what we did last time. And like I said, we're going to come back to some reference triangles later as well. But let's go back to those quadrant angles. 0 and 90 are examples of those quadrant angles that we talked about. Those are kind of a little bit special. But notice that when we talked about being on the y-axis, you don't go left or right at all. So your cosine would be 0. And then your sine would be 1. If you're on the x-axis, you don't go up or down at all. So your cosine would be 1 and your sine would be 0. In that case, it's flip-flop again. Okay. So as we start rotating to different places, we just need to know, are we going to get 0, or are we going to get a positive 1, or we can also get a negative 1 if we go left for cosine, or a negative 1 if we go down for sine. Okay? So it's just a matter of, do we go right and up, or right or up, or do we go left or down to figure out if we got positives or negatives. So let's see if we can do a couple more of those. This one says tangent of 3 pi over 2, right? Really, I'm interested in pi over 2 and see what happens, and then worry about the positive and the negative, right? But again, tangent can be written as sine over cosine, correct? So let's do that first. Because again, you could always boil things down to sine and cosine, right? Now let's think about the pi over 2 reference idea. If you got a pi over 2 reference angle, where are you? Yeah, y-axis, right? If you're on the y-axis, you didn't move left or right at all. So what's the cosine equal to? 0, right? If you don't move left or right at all, the cosine is 0. So hopefully you see you've got a problem already, right? But before we do that, let's see if we can figure out the numerator, okay? Pi over 2 is your reference angle. Sine of pi over 2 is 1, right? But 3 pi over 2, where have you rotated? Yeah, 270 down here, right? So instead of a positive 1, what would you use? Negative 1, because you're below the x-axis, right? Now, this is undefined. I really shouldn't say equal. It should say undefined. So the tangent of 3 pi over 2, or in particular, the tangent of pi over 2 is undefined. Because we get that 0 in the denominator. Does that make sense? Do the same thing for cotangent here. And this one's going to require even less work. How do we define cosine or cotangent again? It's cosine over sine. Now notice our reference angle here again is what? Pi over 2, and pi over 2 is this way, right? What's cosine of this way? 0, right? We didn't move left or right at all. So the numerator is going to be 0. Does it matter what the denominator is? As long as it's not 0, it doesn't matter, right? Let's go ahead and figure it out, make sure we know how. Since we're straight up and down, it's either going to be what for sine? 1 or negative 1. Just depends on, are you above or are you below, right? I need negative 7 pi over 2. How many pi over 2s is that? 4. So I got to go 3 more, right? So is it going to be positive or negative? Positive, because we're up again, right? So we get 0 for our answer there. That makes sense? So far, so good? Okay. Let's do the next one. Secant of 4 pi. First, let's just ignore the fact that we've got secant. Let's try to rewrite it in terms of something we know. Secant is equal to 1 over cosine. So we need to figure out where 4 pi lands, right? All right, that's not too bad. All the way around is... So I got to go... That was weird. All the way around is 2 pi, so I got to go one more time. So we're on the positive x-axis, right? We're this way. So is cosine, what's cosine going to be that way? 1, yeah. Good. If it had been 3 pi rather than 4 pi, what would you have had? Negative 1, because your 3 pi would have ended up to the left-hand side. If you would have had one of the pi over 2's, what would you have said? Undefined, because it would have made the denominator equal to 0 again, right? Does that make sense? Let's do the last one. Cosecant is 1 over sine. Now, I like to visualize what's going on personally. Go negative all the way around is 2 pi. Another time around is 4 pi. Another stupid thing. Another time around is 4 pi. So another time around is 6 pi. And now I made a heart. Okay. We have to do it fast. 1, 2, 3, and then halfway around, right? Really, I think they want to draw different shapes. And then rotate the heart sideways. I didn't know it did that, but all right. Anyway, we're on the x-axis, right? If we're on the x-axis, the sine is equal to 0, which means the cosecant is going to be undefined. Yeah, good. Oops, because we get that 0 in the denominator. That makes sense? All right, so notice that we've been using these quadrant ideas to help us get these values. There is a slight, if you care, if you don't, then don't bother with this. There is another mnemonic that helps to remember which trig functions are positive or negative where. So start here and then go around. This just means that they are all positive in this quadrant. Okay, this means that sine is positive in this quadrant, so cosecant would be as well. This one means tangent, that one means cosine. So the way some people remember is all students take calculus. I'm not saying that's the way you should remember it. I'm just saying it is a mnemonic device that some people like to use to say which ones are positive where. Okay. So over here, if you land over here and you're worried about the cotangent, you know it's negative. If you land down here and you're worried about the secant, you know it's negative. If you land over here and you're worried about cosecant, you know it's negative. Because this is cosine and cosine and secant. That's sine and cosecant. That's tangent and cotangent down there. Would have positive signs. Again, if it helps, great. If it doesn't help, ignore it. One of my buddies from grad school hated this when he taught trig. So he's like, it stands for Amnesty Sausage Timbuktu Carjacker. He was making up words because he didn't like it. But anyway, you can do what you will with that. Okay. All right. Any questions on any of those 6 that we did for those? Okay. All right. All right. So again, these next couple of problems are telling us about using reference triangles to help us figure out these other values. Notice that this one tells us that the secant is equal to negative 17 over 15. They're not giving us what the theta is, they're just telling us what the secant value is. They do tell you that the theta is between pi over 2 and pi. And then find the other trig functions. Well, if the theta is between pi over 2 and pi, where is your terminal side going to be? What quadrant? If it's between pi over 2 and pi, it's going to be in the second one, right? Okay. So what this piece of information is telling you is where to draw your reference triangle. Don't need to worry about scale, just need the reference triangle in the right spot. Okay? No one cares about the scale, just trying to get it in the right spot. Okay? Now let's label some sides. You're given secant. What sides of a right triangle can you label if you're given the secant? Adjacent and the hypotenuse, right? Because secant is 1 over cosine, right? So it's adjacent and hypotenuse you're worried about. Which sides are which here? The 17 is the hypotenuse. And remember, we always use positive for the hypotenuse. Think about it as a distance. So what other side can we label? The adjacent, and we'll make that the negative 15, making it negative because we're to the left. Right? Okay. Can you figure out the other side? Yep. What would we use? Pythagorean theorem. We'll save some time. It'll be 8. But you should know how to solve for that, right? Do a squared plus 15 squared is 17 squared. 17 squared is 289. 5 squared is, or 15 squared is 225. Subtract, you'll get 64. Square root, you get 8. It'll be why did I put a positive 8 there rather than a negative? Yeah, because it's going up, right, rather than down. Yeah, that's why I put a positive rather than a negative. So now from this, we should be able to figure out the other trig functions. So I want sine of theta, cosine of theta, tangent of theta, cotangent of theta, cosecant of theta. Well, one of those I didn't need a triangle for. Which one didn't I need the triangle for? The cosine, because it's the reciprocal, right? That's just negative 15 over 17. But does it match with what the triangle says? Yeah, we did adjacent over hypotenuse, right? So it matches what the triangle said. We didn't need the triangle, but the triangle verifies what we had. How about sine? 8 over 17. Tangent is? Yeah, 8 over negative 15, because we did opposite over adjacent. Now that we have those, we can do the others by doing the reciprocals, right? Cotangent will be good, and cosecant will be 17 over 8. And again, those match with what ratios are on the right triangle if you were thinking about it in terms of reciprocals. Questions on that one? We'll work on the next one for a minute or two, and then we'll chat about it. We're going to talk about this one? Yeah? Nope. Maybe? Yeah. All right. This one tells you where the terminal side of theta is. This is in quadrant 3. So I might as well draw my triangle down here. You're given the cotangent. So what sides can we label? Yeah, the adjacent and the hypotenuse, or the adjacent and the opposite, right? What would you label then? The adjacent's going to be, and the opposite will be negative 24. Good. Both of them are negative in this case, right? Because we're in quadrant 3. We went left, so we have negative 7 for the adjacent. We went down, so we have negative 24 for the opposite. What other side can you figure out now? What news? You used Pythagorean theorem and got 25. Hey, I made nice numbers. What a surprise. All right. Now that you have the triangle, now you should be able to read the other ones off the graph, or off the triangle, right? So sine, cosine, tangent, secant, cosecant. Again, one of those you didn't really need a triangle for. Which one didn't you need the triangle for? And the tangent, right? It's going to be 24 over 7 is just the reciprocal, right? But again, you can see it from the triangle, right? We just didn't need to need the triangle to get that one. All right, what's sine going to be? So is negative 7 the adjacent side or the opposite side? Yeah, so it'll be negative 24 over 25, right? And then cosine will be the negative 7 over the 25. Now the other ones are reciprocals, but again, you can read them from the triangles as well. Secant's going to be good, and cosecant
25 over negative 24.
good. This okay? Not too bad? Okay, cool. All right. Do you want to see another one, or are we okay with that? I can make up another one if you want. Good. Not good. Don't care. All right. Let's go on then to the next concept. This one asks us to look at area of a triangle. Okay. Interesting. What's your typical formula for area of a triangle that you have? Yeah, 1/2 of the base times height, right? Okay. We're actually just going to end up using that exact same formula here. We're just going to write it with a trig function in it to help us get one of the sides. Okay. So the way I've got this triangle positioned on the paper, what do you think we might want to use for the base, just by looking at the positioning of it? The B, right? Was kind of like what the base would be. Really doesn't matter, right? But usually you think of the bottom as being the base, right? So I drew it that way on purpose. So I would need the height. But remember, for triangles for height, you mean perpendicular height, right? So you mean this way. If I want the height, I need the distance from the vertex that's not on your base to the base, right? That's what we mean by height. Okay. Now let's suppose that I'm given A and B, and then the angle between them. Can you figure out what H is in terms of the angle and one of the sides? Yeah, which one do you want to use? Do you want to use the A or the B? Now remember, this B represents the whole thing, right? Do you want to use the A or the B to help us get the height? The A, right? Because my B isn't part of that triangle, is it? Okay. The A is part of the right triangle, but the B is not. Okay. All right. So what trig function is going to relate the theta, the H, and the A? Sine. What's the relationship? Yeah. So sine of theta is H over A. We are given A and we're given theta. We need H. So we'll solve for the H. So your H is A sine theta. Now I have the height and I have the base. So the area of your triangle, remember we said is 1/2 base times height, right? Your height is a sine of theta. So you get 1/2 AB sine theta as another, just it's an equivalent form. We're just giving a way to figure out what the height is. Typically, you're not given the height, you're given something about the sides of the triangle, right? Okay. There's nothing special about necessarily A and B. Really what you're given, notice the relationship in the triangle. I've got two sides and their included angle, right? I've got A, I've got B, and the angle between them. Two sides and an included angle. Remember from geometry, you had a congruence theorem, side, angle, side. This is an example of one of those ideas. We're going to come back to those congruence theorems later on, a few sections from now. I just want to mention it. But again, nothing special about the way they're labeled. Just two sides at an included angle is what you need to figure out the area. Okay. So remember again, ordinarily, when you label the sides and the angles, especially when we've got Greek letters, if you've got A, B, C, I'm just putting them wherever, your little letters are going opposite the vertices that they correspond to. And we use the Greek letters for the different angles that we have. So in this problem, it says we've got B and C. The angle included between B and C is alpha. Okay. So we really do have two sides in the included angle. So your area will be 1/2 times 12 times 9 times sine of 130 degrees. You get 54 sine of 130. Is 130 degrees a special angle that we know? I don't think it is, right? Reference angle there would be 50 degrees, and 50 is definitely not one we know, right? So if you had one like this, especially in WebAssign, it would want you to type it in your calculator. Get a decimal approximation for that one. Yeah.
Did you put in B or C? The equation you had earlier was 1/2 AB sine, and then this one you C.
So again, it doesn't matter which the sides are as long as you have the included angle. So you can do 1/2 AB sine of gamma if you're given the angle at C. You can do 1/2 AC sine of beta if you're given the angle at B. And you can do 1/2 BC sine of alpha if you're given the B and the C. Yeah, so there's nothing special about A because you can always relabel, right? So there's nothing special about the fact that we've got A and B. We just need those two sides and the angle between them. But it has to be the angle that's in between the two sides you're given. But as long as you have that, then you're good to go. What did you get for that, by the way? If we put it in a calculator, I saw some people typing it in. Sounds good to me. I estimated it to be around 40 in my head, so. Know what others got when I typed it in? Mm-hmm. Okay, cool. How would we do the next one then?
I'm still kind of confused on the angle part on the last one. Like why did we not use AB instead of when we use AC? Can you go over that one more time?
For
The last problem.
this one we just did?
Yeah.
Okay. So again, when we have the triangle, the labels don't matter as long as we're doing the sides and what's included. So again, we've got our standard is that if we've got triangle ABC, our little a is across from alpha, our little b is across from beta, our little c is across from gamma. So we were given, if I can get this to open without going crazy, we were given B, C, and alpha.
Okay.
So we've got the two sides and the included angle. So I can just plug it right into the formula when I have that. Yeah. I know when we came up with the formula, we used A and B, but the letters don't matter because I could have gone back up here and just relabeled everything as different letters, right? There was nothing special about them. The important part is the relationship between the sides and the angle. If I were given B, C, and beta, I'd be in trouble because I wouldn't be able to use that formula. If I were given A, C, and gamma, I'd be in trouble. I have to have the one that's in between them. Does that help?
Yeah.
Okay, cool.
Appreciate it.
Yep, you're welcome. So in this one, what would we have? Is beta in between A and C? Are we good for that? Okay, so we can just plug it in again. You'd have 1/2 times 20 times 18 times sine of 25. Yep. And that gives us what? About? Okay. Yep. Happy with that? This one's a little bit different. This one says that we have a triangle with two sides, and the area is 85. And it asks us to find the angle between the two. This is actually a little bit trickier because it talks about a concept we haven't mentioned yet, but we'll get to it. All right, so if we have two sides and the area, what equation can we set up here?
85 equals 1/2 times 45 times 25 times sine of theta.
Good. We good with that? How do you think we should attack this one? Get sine of theta by itself, right? So multiply both sides by 2 and divide by that product of 45 and 25. So sine of theta would be that. I didn't feel like multiplying 45 and 25 in my head. That okay? Now, we need to be able to undo the sine function. Now, we haven't talked about what we mean by undoing the sine function yet, but we can do this with a calculator for the time being. And talk a little bit more about what we mean by the operation here in a little bit. So, if you had, say, theta squared instead of this on this side, what would you do to undo the square? Theta square root, right? If I had, say, natural log of theta on this side, you would do e to that power on both sides, right, to undo the log. Basically, we need to undo the sine function, right? And there's a button on your calculator that does that. There's the inverse sine function. It's right, should be right above your sine key. Okay, so you would do inverse sine of that value, whatever that is in your calculator. And then there's an interesting property of this, and then we're going to leave it alone until we get back to it when we start talking about the inverse trig functions. Put this in your calculator. It doesn't matter if I do it degrees or radians. Degrees is what we've been in, so might as well do it degrees. Did you get a value for that? What'd you get? 8.69 degrees. Okay. So what others got for that? Oh, okay. All right. So it should be a 25. Looks like I wrote 75 there. There we go. All right. So 8.69-ish. All right. Here's the interesting part. So that gives us the angle that we want, but there's actually two triangles this would work for. This is interesting. The reason for that is that you could have had a triangle where the angle between the two sides was tiny, right? Something like this, where this was your theta, and then you had 45 and 25 here, right? We agree with that? But you could have also had a triangle that went this way. And this one being 180 minus theta. And you would have also got an area of 85. The reason for that, of course, is if my theta, well, let's do it this way. If this is 180 minus theta, I make my reference triangle. This is now theta, right? The sine of 180 minus theta is the same as the sine of theta because of the reference angle, or the reference triangle here. Okay. So this problem actually has two answers that you could use. I could do the 8.69 degrees or 180 minus the 8.69 degrees, and you get the same answer for the area. Okay. We're going to talk more about that when we get to inverse functions later. I just wanted to mention that is a possibility for this one. All right. Let's see if we can do these last two here pretty quickly. We have a rhombus. Rhombuses have 4 congruent sides. They tell us that each side is 19, and the angle, one of the angles is 120, and it wants the area. So if I draw the picture, however you want to draw the picture, close enough. Every side is 19. So in particular, I would have those two sides as 19 with an included angle of 120 degrees. Looking at this, how could you get the area of the rhombus? What do you think you would do? Cut it in half. Good. And the other side looks exactly the same, doesn't it? So what would you get for the area of the rhombus in this case?
Would this be sine of 120 times minus 19 squared?
Okay. And we don't need to worry about the 1/2 because we have 2 of them, right? They're 2 identical triangles, 2 congruent triangles. So you'd have 2 times the half. The 19 squared comes from the fact that the 2 sides are the same. Right? What would be the reference angle for 120? 60. Do we know sine of 60?
Yes.
Yeah, it's what? Square root of 3 over 2. 19 squared is what? 381. So you would have 381 root 3 over 2. Is an exact answer. 381? 361. I said 381. I thought it. Thanks. 361 over root 3. Again, you could get an approximation in your calculator. I just want to make sure we reviewed the fact that you should know how to do sine of 120. and get an exact value. Is that okay? Let's talk about how we would approach this last one. Regular hexagon. How many sides does a hexagon have? 6. So you would have 1, 2, 3, 4, 5, 6 sides. Regular means what?
It's the standard one. I don't know.
Okay, so I like that, a standard one. So what do you think it means if we want to be like a standard one? Yeah, all the same size and all the same angles, right? That's what regular means, is all the sides are congruent, all the angles are congruent. Okay, cool. So I know that all the sides are congruent, right? I know all the angles are congruent. Probably an easier way to do it, at least in my mind, an easier way to do this is think about everything coming out of the center this way. I would have 6 triangles coming out of that, wouldn't I? All the way around would be, if I went for the angle, all the way around would be 360. If I've got 6 triangles going all the way around, this angle is going to be 60, right? Agree with that? These 2 sides are the same, right? Because they're coming out from the center of the center of the hexagon. That's all. Everything's nice and equal here, if you will. These 2 sides are the same. Makes those 2 angles the same. Those 2 angles have to add up to 120, right? So both of those angles are 60 degrees. Now, what kind of a triangle did I make? Equilateral. So this is also 10 and 10. So can I find the area of that small triangle we just drew? Yeah, I've got 2 sides and the included angle, don't we? So the area of the whole thing will be 6 times a half of 10 times 10 times sine of 60. I've got 6 small triangles. Each one we can do by doing 1/2 times the product of the sides times the sine of the included angle. Yeah? Sine of 60 degrees again is what? Root 3 over 2. So we're going to get what? 300. Oops. And it's root 3 over 2, but that's 300, isn't it? So we get 150 root 3 when we're done. So again, we just used the information that we had to find the area of one triangle, and there are 6 in here. So we just multiply it by 6. Does that make sense? All right? Pardon me. All right, so on Friday, we'll have a quiz over 6.2 and 6.3. We'll do that on Friday. Wednesday, we'll get into, I think we're doing graphs of functions next. So we'll talk about that on Wednesday. But I want to make sure that we're all on the same page with the last 2 sections that we talked about. So 6.2 and 6.3, doing the values of the trig functions. We'll have a short quiz on that on Friday. All right. Have a good one. We'll see you on Wednesday.